the next example, consider the following program segment. The program segment is a toy or dummy algorithm that has two nested loops. The outer loop is a for loop, the iterator is I and it is simple. And the inner loop is a while loop, the iterator is j and it is not simple. In fact, it is divided by 2 in every iteration. The first part of the question is asking to find the basic operation. The second part of the question is asking to find the efficiency of the algorithm. So what is the basic operation of this algorithm? As we've mentioned before, the basic operation can be found in one of the statements inside the innermost loop of the algorithm. In our case, it is the while loop. So why one of the statements inside the loop, not the condition of the loop? Because in general, if you have a loop that depends on an iterator, like a for loop, or other loops like while, do while, repeat until, and so on, then conceptually it does not make sense to select the basic operation from the condition or update statements of the loop, because these statements are part of the loop operation, not part of the problem solution. Therefore, in our example, the basic operation is the addition operation at line 5. It is not the comparison operation at line 4, nor the shift operation at line 6, because these operations are part of the loop operation, not part of the body of the loop. Now let us find the efficiency of the algorithm by counting how many times the basic operation is executed. Now to find the time efficiency, we need to find the number of addition operation of the statement inside the while loop. And to do that, we need to count how many times the inner loop is iterated. This can be done by listing all values of j received by the condition in every iteration. So here we write the time efficiency, Tn, is equal to the summation of the outer loop that goes from 1 up to n over 2, and the summation of the inner loop, which is j. Now we need to list all values of j received by the condition in every iteration. The first value is n, and then when it is divided by 2, it becomes n over 2. Again, if this n over 2 divided by 2, we get n over 2 square. Next iteration, it will be n over 2 raised to power 3, and so on. In the last iteration, the value of j will be equal to n divided by a number that is a power of 2, which is 2 to the power of k. And inside the summation, we have 1. This summation is equal to summation I equal 1 up to n over 2, and j will start from 0 up to k. Summation of 1. As you can see, that n is divided by 1, and 1 is equal to 2 to the power of 0, and 2 is equal to 2 to the power of 1. So this is why j starts from 0, it goes up to k. Now to evaluate this summation, this will be equal to summation I goes from 1 up to n over 2, and for the inner summation we have 1, so the answer will be k minus 0 plus 1, so it will be k plus 1, and since k plus 1 does not depend on I, we can take it outside the summation and replace by 1, and this will be equal to k plus 1 summation I 1 up to n over 2 1, and this is equal to k plus 1 multiplied by n over 2 minus 1 plus 1, which is equal to n over 2. We will label this formula by 1. Let us first find the estimated answer. So for the estimated answer, what we will assume? As you notice that in the condition of the while loop, we have j greater than or equal to 1. That means eventually we will assume that this value will be equal to 1. So here we will say assume that n over 2 raised to power k is equal to 1. And this n over 2 to the power of k is the last value of j. So we assume it reaches 1. Now solve for the value of k. So what we will have here, we will say that n is equal 2 to the power of k. Take log of 2 both sides, so we have log 2 of n is equal to k. Now substitute into formula 1. So we have Tn is equal to k plus 1, and the value of k is log 2 of n. So we have log 2 of n plus 1 multiplied by n over 2. And this is equal to n over 2 log 2 of n plus n over 2. And if we want to find the asymptotic notation for this formula, this belongs to big theta of n log of n. Now for the exact answer, the loop condition is j greater than or equal to 1. And the last value of j is equal to n over 2 to the power of k. So we substitute for that. So we will say that n over 2 to the power of k is greater than or equal to 1. Either we say that the value of n over 2 to the power of k is bounded between 1 and 2, or we can transform this inequality by saying that n is greater than or equal to 2 to the power of k. So let us work on this inequality. As we discussed before, since the value of n is an integer, so we can write it as 2 to the power of k less than or equal to n, less than 2 to the next iteration of k that makes the condition false, k plus 1. Take log of 2 in each part of this inequality. So we have k less than or equal to log of 2 of n less than k plus 1. And in fact, this is the floor of log 2 of n equal to k. Now substitute into formula 1. In formula 1, we have k plus 1 multiplied by n over 2, and this is equal to the floor of log 2 of n plus 1 multiplied by n over 2. This is equal to n over 2 multiplied by floor of log 2 of n plus n over 2. And again, by the asymptotic notation, this belongs to big theta of n log of n. So both the estimated and exact answers belongs to big theta of n log n. So what is the conclusion of this example? The conclusion is that if the iterator is divided by a constant, then the number of iterations is log of n, and the base of this log is the constant. So in this example, the iterator is divided by 2. So the answer is log of n base of 2. And if it is divided by 3, then the answer is log of n base of 3. And if it is divided by 5, then the answer will be log of n base of 5, and so on. In the next example, we have also a toy or dummy algorithm that has a simple for loop. The iterator I goes from 3 to n. Inside this for loop, it has an if and else statement. If the condition is true, we have another loop, which is a nested loop. The iterator is j, goes from 1 to I. And if the condition is false, which is the else part, we have only one statement that is adding 2 numbers. The question is asking to find the basic operation and find the time efficiency of the algorithm. In this example, the algorithm has a simple for loop that goes from 3 to n. And inside it, it has an if and else statement. As we've mentioned before, to find the time complexity of an if and else statement, Then you need to find the time complexity for the true part when the condition is true. And also you need to find the time complexity for the else part when the condition is false. Then combine the two results and take the maximum. So what are the values of I that make the condition true? The condition says that I mod 3 equal to 0. So basically any value of I that is divisible by 3 will make the condition true. By going over all numbers from 3 to n, any value that is divisible by 3 will make this condition true. So let us list these values. So here we write I mod 3 equal to 0, and in here we will list all values of I that make the condition true, and these are equal to 3, 6, 9, which are multiple of 3 represented by 3k. Any other value of I will make the condition false, so we will list them here, and here we will say that the condition is false for the values 4 and 5, 7 and 8, and these are of format 3k plus 1 or 3k plus 2. So these numbers, when they are divided by 3, either the remainder is 1 or the remainder is 2. So first we will find the time complexity for the true part. And then we will find the time complexity for the else part. We will combine the two results and take the maximum. So let us start with the true part. By going to the algorithm, this is the true part. And it has a for loop that goes from 1 to I. And inside this for loop, there is a statement that has the addition operation. So we will consider the addition operation as the basic operation. And how many times this basic operation is executed. So we will write T of n for the true part is equal to. For the outer loop, we have to count all values that are multiple of 3. And for each value that is multiple of 3, we have a for loop. This can be formulated by the following summations. Summation for the outer loop, the values of I are 3, 6, 9, up to 3k. And for each value of I makes this condition true, we have a for loop that can be represented by the summation j equal 1 up to I. And inside this for loop, the basic operation is executed once. And now we need to evaluate this summation. And this will be equal to summation I equal to 3, 6 up to 3k. And the inner summation is evaluated to I. Why? Because we have a summation of 1. And you know that for evaluating a summation of 1, the answer will be the last value minus the first value plus 1, which will be equal to I. So first you need to evaluate the inner summation, and then the result will be part of the outer summation. So now we have this summation, and it is not equal to 1, so this is not a unity summation. So we cannot transform it into summation I equal 1 up to k1 is equal to k. This is wrong, because what we have inside the summation is I, it is not 1. So we are not counting how many values of I do we have. We are adding those values. So the answer will be, and this is equal to 3 plus 6 plus 9 plus 3k, which is the last value. So for each value of I, we are adding this value. Now take a 3 as a common factor in this formula, and you will get 1 plus 2 plus 3 up to k. And this is an arithmetic summation. This is equal to 3 summation of I that goes from 1 to k of I. This is equal to 3 multiplied by 1 over 2 times k plus 1. And this is equal to 3 over 2 k square plus k. And we will label this formula by 1. Now the condition of the loop of the for loop is I less than or equal to n. And the last value of I in the last iteration is equal to 3k. And this will lead us to 3k less than or equal to n. To find the estimated answer, then you need to assume that these values are equal. I mean n is a multiple of 3. We will say assume 3k is equal to n. Or in other words, assume n is equal to 3k, which means multiple of 3. Now solve for the value of k. So k is equal to n over 3. Substitute into equation 1. So the time complexity for the true part is equal to 3 over 2 n over 3 square plus n over 3. And after simplification, this is equal to n square over 6 plus n over 2, which belongs to big theta of n square. To find the exact answer, from the condition of the for loop is 3k less than or equal to n less than 3k plus 1, which is the next value of I that makes the condition false after the last iteration. And divide each part in this inequality by 3, we will get k less than or equal to n over 3 less than k plus 1. Basically, what we will get from this inequality, the floor of n over 3 is equal to k. Now, if you substitute into formula 1, so the time complexity for the true part is equal to 3 over 2. We have a floor of n over 3 square plus the floor of n over 3. And again, this will belongs to big theta of n square, because this is the addition of two formulas. The first formula is quadratic, the second formula is linear. Then according to the asymptotic notation, we have to select the function that is growing faster. This function is the quadratic function. Now let us go for the else part, which is for the false part. We go back to the algorithm. All values that are multiple of 3 make the condition true. Other values make the condition false. So how to count these numbers? Notice that in the else statement, we have only a single statement, and it has an addition operation. So basically, we will consider this addition as the basic operation. So how many times this addition or the basic operation is executed? It depends on what are the values of I that make the condition false. Remember that if I is multiple of 3, the condition is true. And if it is not multiple of 3, the condition is false. So from 3 to n, if we exclude all values that are multiple of 3, will give us the values that are not multiple of 3 and make the condition false. This can be formulated by a summation by counting how many numbers do we have from 3 to n minus those numbers that are divisible by 3. Let me show you how. So if we label this one for the true part 1, and now we will go for 2, we will have t false of n is equal to. So how many numbers of I do we have in total? It will be summation. Value of I starts from 3 up to n of 1. So these are all numbers from 3 to n. Minus those numbers that are divisible by 3. So I equal to 3, 6, 3k, and we have the summation of 1. Now by evaluating this summation, this is equal to n minus 3 plus 1 because we have a unity inside the summation, and the answer will be n minus 2. Minus. Now we need to count how many numbers do we have for I. So we can transform this non-standard summation into a standard summation by saying I goes from 1 up to k of 1. And this will be equal to n minus 2, and this is a summation for a unity. So k minus 1 plus 1 is equal to k. So this is equal to n minus k minus 2, and we will label this formula by 2. So the condition of the loop is I less than or equal to n. And since the last value of I is 3k, so we have 3k less than or equal to n. So for the estimated answer, assume n is equal to 3k. So assume these two are equal. Solve for k. K is equal to n over 3. Now substitute into formula 2. So we have the time complexity for the false part of n is equal to n minus n over 3 minus 2. This is equal to 2 over 3n minus 2, which belongs to big theta of n. Now for the exact answer, the condition (3k less than or equal to n), 3k less than or equal to n less than 3k plus 1. Divide each part of this inequality by 3. We will get k less than or equal to n over 3 less than k plus 1. And this is the floor of n over 3 equal to k. Now substitute into formula 2. So we will have t for the false part is equal to n minus the floor of n over 3 minus 2. And again, this belongs to big theta of n. Now the time complexity for the whole if and else statement. So we will say that this is a 3. So Tn is equal to maximum between the two time complexity, the true part and the else part. Here we have the true part, T of n true, and here we have for the false part, Tn of false. And we need to find the maximum. We will substitute the estimated answers, and we will have n squared over 6 plus n over 2. And for the false time complexity, we have 2 over 3 n minus 2. The first formula is quadratic. Second formula is linear. So the quadratic function grows faster, and you can prove this by using limits. So the answer here, we will have the maximum, which will be the time complexity for the true part of n, and this is equal to n squared over 6 plus n over 2, and this belongs to big theta of n squared. This is the time complexity for the algorithm when we consider the addition inside the innermost loop of the true part of the if and else statement as the basic operation. There is another solution for the time complexity of the false part of the if and else statement by considering all values of I that are not divisible by 3. Let me show you how to do that by going back to the beginning of our analysis. When we started the analysis, we've listed all values that are divisible by 3 that made the condition false. And also we have listed all values of I that are not divisible by 3 that made the condition false. So these are the numbers not divisible by 3. And they are of two different formats, 3k plus 1 or 3k plus 2. So we will list each of these numbers separately. So this is step 4. First we will list all values. When they are divided by 3, we get a remainder 1. Starting from 4, you add 3, you get 7. You add 3, you get 10 of type 3k plus 1. And the rest that are not divisible by 3, starting from 5, we add 3, we get 8. You get 11. And these are of type 3k plus 2. The values of k in each of these numbers are not the same. So in the analysis, we need to give them different names. So the first k, we will call it k1. The second k, we will call it k2. So the time complexity for the false part of n will be formulated with the following summations. For the first type of numbers, I equal to 4, 7 up to 3k1 plus 1, plus the second type of numbers, 5, 8, 3k2 plus 1 of 1. We will replace these summations by standard summations. So these summations are equal to summation I starts from 1 up to k1 of 1 plus the other summation also starts from 1, it goes up to k2 of 1. Evaluating these two summations, we get k1 plus k2. We will label this formula by 3. We will first consider the estimated answer. And we will assume the following two assumptions. For the first assumption, we will assume that n is of type 3k1 plus 1. Solving for k1, we get n minus 1 over 3. And for the other type of numbers, we will assume n is equal to 3k2 plus 2. Solving for k2 will be equal to n minus 2 over 3. Substitute into formula 3. So we will say that the time complexity for false of n is equal to k1 plus k2. So it is equal to n minus 1 over 3 plus n minus 2 over 3. And this is equal to 2n minus 3 over 3, which is equal to 2n over 3 minus 1. And this belongs to big theta of n. And now for the exact answer. Then we have 3 k1 plus 1 less than or equal to n less than 3 k1 plus 1 plus 1. Subtract 1 from each part of this inequality. We get 3k1 less than or equal to n minus 1 less than 3k1 plus 1. Divide each part of this inequality by 3. We get k1 less than or equal to n minus 1 over 3 less than k1 plus 1. And from here, we can say that the floor of n minus 1 over 3 is equal to k1. Now for the other numbers, we have 3k2 plus 2 less than or equal to n less than 3k2 plus 1 plus 2. Subtract 2, we get 3k2 less than or equal to n minus 2 less than 3k2 plus 1. Divide by 3, k2 less than or equal to n minus 2 over 3 less than k2 plus 1. And here we have the floor of n minus 2 over 3 equals to k2. Substitute for these values into formula 3. So we have the time complexity for the false part of n is equal to floor n minus 1 over 3 plus floor n minus 2 over 3. This belongs to big theta of n because big theta of n for this equation is n and big theta of this equation is also n. So both belong to big theta of n.